Okay, so now we're on section 8.3, which is on conditional probability. We already talked about this some in class, but let's, let me just start from the get-go with sort of similar examples to what we did. So here's a motivating example. Let's suppose that you are taking a 4-question true, false quiz. Maybe your history professor is like, hey, I want to see if you did the reading last night, so let's see if, you know, blah, 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 whatever. Now, it might be reasonable to assume that 2 of the answers are true and 2 are false. Because, maybe the professor thinks that that's making it random. To tell you the truth, that's actually not random. That's putting some sort of structure on what the answers are, which is that 2 of them are true and 2 of them are false, and completely random would allow for all 4 to be true or all 4 to be false or 3 to be false or whatever. Anyways, but let's just assume that this is what's going on. So, and furthermore, let's say, let's say that you look at the first problem, you look at it and you're like, I don't know what it is. So you're going to have to guess. You might as well guess something because, hey, if you get it wrong, too bad. If you get it right, then you get some points. So I'm going to guess. Let's guess true. So what is the probability that I am right? So what is the probability that the first question is true? Well, let's see what that is. So we're going to assume that any arrangement of the answers is true, is equally likely, so our sample space is going to consist of this. The first 2 could be true, and the second 2 could be false, or the first and the third could be true, and the other 2 are false, or the first and the last could be true, and the other 2 are false, or the first could be false, and the second and third could be true, or the second and fourth could be true, or the third and fourth can be true. So that is our sample space. These are all the possible ways that the test can be if there are 2 trues and 2 falses. And what set are we looking at? Well, the event we're looking at is that the first is true, which are these first 3 outcomes. So the probability that the first is true, so let me just write that, the first is true, is the number of things in the set E divided by the number of things in the set S. And the number of things in the set E, you can just count them as 3, and the number of things in the set S is 6. I'm going to note that the number of things in the set S is actually 4C2 because you're choosing 2 of the answers to be true and the other ones are then false. You can show that this is 6. Okay. And 3/6 is the same thing as 1/2. Well, that makes sense. Guessing on a true-false question half the time you should be right. But let's suppose that you go to the second question and you know it's false. Great, so you have got a leg up. You actually got the second one right. But let's go back to the first question. Now, let me let F be the event that the second question is false. So the possibilities are true, false, true, false, true, false, false, true, and false, false, true, true. This is the ways that the second can be false. Now, with this knowledge, what is the probability that the first is true now? Well, in some sense, F is now our sample space because we've excluded 3 of the possibilities from S because we know that the second one is false. So now, assuming that the second one is false, that the first one is true, is E intersect F, which is true, false, or true, false, false, true. So this is that the first is true and the second is false. Let's clear this. So the probability that the first is true, let me erase that. If the first is true, since we're knowing that the second is false, is the number of things in E intersect F divided by the number of things in F. We know that F is true, and so we're saying, well, what's the possibility that E is also true? And if you remember, E and F had 2 possibilities, and F had only 3 possibilities. So now this is actually bigger than a half. So you might as well guess, you should guess if you don't know, that this is true. But you really should, go through the rest of the test and see if you know the rest of them first too. But so you should guess true. Okay, cool. So let's see. This is something called a conditional probability. So let me give the definition of a conditional probability. So the conditional probability of E given F, so of some event E given some other event F, at least intuitively, is the probability of E when F happens or assuming that F happens. So what exactly do I mean by when F happens or assuming that F happens? Well, here's a scenario where it's a conditional probability that is with respect to F happening. If I might consider the probability that I have my umbrella on me. This could be the event E versus the probability that I have my umbrella on me when it's raining. And here the fact that it's raining would be the event F. So this is a case where the event I'm looking at is, I'm looking for the relative probability when I know that it's raining, when it is actually raining. Now let's compare that to the other case when we assume something's true. We could say, well, what's the probability that Obama is elected? So that could be the event E versus the probability, oh, that looks terrible, the probability that Obama is elected, assuming, say, Mitt Romney gets the Republican nomination, which in this case would be the event F. So here, this is something that we don't know to be true, but we might assume it's going to be true, and then try to come up with some sort of probability of that Obama is going to be elected, assuming that Romney gets nominated for the Republican nomination. Okay. Now let's we want to get some notation down. So the notation is that when we write the conditional probability of E given F, we write P, and then inside of parentheses E bar F, and we read this as the probability of E given F. We don't say conditional typically when we say this. Now there's also a formula. Now let's remember that when I computed a conditional probability before, I computed it by counting the number of things in the intersection of the two events divided by the number of things in the assumed event. But this only works when we have equally likely outcomes. Generally, what we have to do is instead replace n with p, which is something that we've been doing a lot. The probability of E and F, or the probability of E given F, is the probability of E and F divided by the probability of F. So this is generally. This is what we do generally to compute this. And the idea is really that F is our new sample space. That's what's really happening when we do this. So dividing by the probability of F normalizes things. It normalizes the probabilities so that F is the new sample space. Okay. And sort of a Venn diagram picture of this would be something like, here's E, here is F, and what's happening when we do a conditional probability, it's something like all of a sudden F is becoming the sample space and we're ignoring everything else outside of F. And that also explains why we only care about E intersect F, because E intersect F is the portion of E that's inside of F. So if we're looking for the probability that E happens, we're already assuming that F has happened. So we're only concerned with this bit. So that's okay. Now let's do a couple of examples of this. First of all, let's do an example where we do not have equally likely outcomes. So I used to live on the F in Brooklyn, and so when I went home from Columbus Circle, I had two options. I could take the B or the D to West 4th Street and transfer to the F. I could take the A or the C to West 4th Street and transfer there, but the F takes a little bit longer from West 4th Street than the A or C. If I took the A or the C, I would go to, that looks like an H. That is supposed to be a 4. So West 4th Street, and if I took the A or C, I would take it to J Street. Now the A and the D run on the express tracks, at least at Columbus Circle, and the B and the C are on the local tracks. And so what this really affects is how often the A and D show up and how long the B and C show up. Yes, the B runs express after Columbus Circle, but let's just, look at it like this. So the probability that I get on the A is going to, used to be like 35%, and the probability that I got on the D was about 30%. The A came 35% of the time, the D came about 30% of the time. Now, if I got on the local tracks, well, the B came first about 20% of the time, and the C came first about 15% of the time. So this is, which train I'm taking. So let's ask a question. Let's say that E is the event that I get on the express train, or get on the express track. So that means that this is a comma D, and let's let F be the event that I get off at West 4th Street, which is going to be B, comma D. Okay. Okay, so let's ask a couple of questions. First, let's consider first, uh, given I get off at West 4th Street, which is F, what is the probability I got on the express train or on the express track at Columbus Circle? Well, this is the probability, and that is the event E. So it's the probability of E given F, and by definition, this is the probability of E intersected with F divided by the probability of F. Now, E intersect F, that's the express track that gets off at West 4th, that's only the D. And the probability I got on the D is 0.3, so this is the probability of the D. What's the probability I got off at West 4th Street? Well, I could have taken the D, which is 0.3, or I could have taken the B, which is 0.2. So I get 0.3 divided by 0.5, which is 3/5, or 0.6. So there's a 60% chance that I got on the express track given that I got off at West 4th. So if you saw me hanging around at West 4th and asked, hey, what train are you waiting for? And I'm like, the F, you could assume that there's a 60% chance that I took the D. Okay, let's ask a sort of a backwards question. Let's say given that I got on the express track, what is the probability I get off at J Street? Say you follow me in Columbus Circle because you've got something very important to tell me. I don't know what. There's an axe murder at my house and you got to warn me. And you miss me though. You run down to the platform and you see a train leaving on the express track, but you're not sure which one it is. So you've got to make a decision. Is he going to be getting off at J or West 4th? I want to run to one of these stations and find him before he goes home. Okay. Well, getting on the express track is the event E. Getting off at J Street is the event F prime, because F is getting off at West 4th. So this is the probability of F prime given E. And by definition, this is the probability of F prime intersected with E divided by the probability of E. Now the probability that I got off, and let me sort of come down here, the probability that I get off at J Street and took the train that came on the express track, well, the only way of doing that is the A, so that possibility is 0.35. That's getting on the A. Whereas getting on the express track, I could have gotten on the A, which is 0.35, or I could have gotten on the D, which is 0.3. So this is 0.35 divided by 0.65, and this is approximately equal to, well actually this is literally equal to, sorry, I've got an eraser, why don't I use it? This is literally equal to 7 out of 13. And it's just a little bit bigger than a half, so you're probably not going to be able to make the correct guess as to where I'm going to be. You can guess that I'm going to be at J Street 7/13 of the time, so you might as well try to go to J Street to stop me, but there's a good chance I'll be at West 4th. Anyways, you might as well hang out at J Street and wait for the F to show up if I don't show up on the AC. Look for me in the F, jump on, say, "Don't go home, Professor Bragg, axe murderer." Good. Be very nice of you. Let's do one more example, and let's assume that we're sort of given a table. Now this is literal data from voters for the president in 2008. There were three ways people could register. They could be Democrats, Republicans, or Independents, and most all of them voted for McCain or Obama, so we might as well just assume that everybody voted for McCain or Obama. Now, out of all of the people who voted, 35% or 0.35 probability were Democrats who voted for Obama. 0.4, 0.03 were Republicans voting for Obama, so that's 3%, and 0.15 were independents voting for Obama, that's 15%. Now, Democrats voting for McCain, 4% of the entire voting population were Democrats voting for McCain. 29% of the entire voting population were Republicans voting for McCain, and 14%, 0.14, were independents voting for McCain. So I can ask, let's compare these probabilities. What's the probability that somebody voted for Obama? Well, I would just add up all of the numbers in the first row because those are all the different percentages of people voting for Obama. So it's 0.3, that's not a 3, it's 0.35 plus 0.03 plus 0.15, and that is equal to 0.53. So 53% of the people voted for Obama. But how about I ask you, what's the probability that somebody who voted for Obama, given that they're a Republican? Well, this would be the probability that somebody voted for Obama, given that they're Republican, divided by the probability that they're a Republican. Now, voting for Obama and being a Republican, that is just this first row, second column, 0.03. But the probability that a voter was Republican is 0.03 plus 0.29. So 0.03 plus 0.29. That works out to, I've got the numbers already, to 0.03. Yeah. Let me just say that the bottom over here is 0.32. Well, 0.03 divided by 0.32, this is approximately equal to 0.09. So only 9% of Republicans voted for Obama. So I can figure that out from this data right here. Okay.